Good afternoon, everyone. Welcome to week 10 problem solving sessions on regression analysis. I'm Shreya, one of the TAs for this course, and today we'll be discussing some problems based on the concepts discussed during week 10, and we'll also touch up on the previously discussed topics. We'll see in due course, those will come handy while solving problems. So without any further ado, let's get started. Okay, so this week it was all about so far what have we learned? Last week we learned about something known as week 9 was all about generalized least squares. Okay, these were the cases which came in handy when the normal assumptions were not holding true. Okay, the normal assumptions, like in the sense that when we see that there's a pattern in the variance, like variance of epsilon I is not equal to sigma square for all I. Okay, those sort of situations where we found that there was a certain kind of deviation from the assumptions of a linear model, then we used generalized least squares, and it is very similar to the OLS in the sense that they just incorporate an extra term in the middle, in the sense if we have something like y equal to x beta plus epsilon, and our OLS estimate, one second, and we had our OLS estimate as x transpose x inverse x transpose y, then beta had GLS was nothing but x transpose v inverse x transpose v inverse y, where v is what? V is the variance covariance matrix. Okay, so this is something that we learned. So what was V? Variance of epsilon, in the case this is sigma square V. Okay, so if V equal to I, that all variances are equal, we actually land up at this model. Okay, so in generalized least squares, what did we do? We transformed this to some y star equal to x star beta plus epsilon, and then we applied OLS on transformed model. Is it okay? And then we, after applying these sorts of transformation, we got final whatever we got the GLS estimate of beta as this thing, and also we found out that variance of beta hat GLS is nothing but sigma square x transpose v inverse x inverse, and whereas variance of beta hat OLS was actually sigma square x transpose x inverse. Alright, so from this model, from the GLS model, if we had to calculate sum of squares due to residuals, then that would be y star transpose y star minus beta hat GLS, because GLS is beta hat GLS is OLS on the transformed model. So this would be beta hat GLS into x star y. Okay, and that if we solve, it would actually come up to this. Y transpose V inverse y minus beta hat GLS. This would be x transpose V inverse y. Okay, so this is S is due to residual, the generalized form. Alright, so this was all about week 9 lectures. So what did we learn in week 10? Week 10 was all about dummy variables. Now, what is a dummy variable and when is it used? So dummy variables are variables which take on value either 1 or 0. Okay, so this d could either be 1 or it could be 0, and the use case is this is used when we have when our predictors are measured in the categorical scale. Okay, when predictors are measured in categorical scale, that is the use case where we actually go ahead to use dummy variables in our regression model and then carry out our analysis. So the simplest possible example would be of, let's say, gender. Okay, so this is a specific this is a dichotomized variable where gender can be usually it can be male or it can be female, or in the sense now if we consider something else as other, then this is also a categorical variable. Okay, so if I want to incorporate this information into my regression model, I would have to resort to dummies. Okay, now how many dummies, what, that we'll see in the next case. Another simple example of dummy variable, let me consider the simplest case that gender is actually male or female. This is the simplest case of two, or let's say I'll not use gender. Let's say I want to categorize educational level. Okay, and one is postgraduate and above, and one category is not, below postgraduate. Okay, so now my question is, let's say, does wage depend on educational level, or in other words, do postgraduates earn more than non-postgraduates? Okay, so if this is my research question, then now in previously what we had previously, we had y equal to beta naught plus beta 1 x plus epsilon. Now this x used to be continuous, but now we don't have that. So now this x is actually categorical. Okay, now if I say that x is my variable, the dummy variable, then x can take two values, one for postgraduate and x can take value 0 for below. Alright, then all we need to do is that in this model matrix, that is x y equal to x beta plus epsilon, this x matrix will be 1 1 1 1, and wherever it is postgraduate, whichever ith individual is postgraduate, that will be 1 and others will be 0. And then once the model matrix is ready, we can just go ahead, use this in our equation and just get values of beta naught and beta 1. Okay, so this is the simplest possible case. Now this was the case where we had one dummy variable. Okay, we could also have cases where we require more than one dummy variable. So the next question is how to choose the number of dummy variables. Okay, so let me go back to that example. So here, that gender example, if we consider male, female and others, then we have three categories. Okay, so when we have three categories, then apart from if we are including intercept, if intercept term is there, then if we have m categories, then we should include m-1 dummies. Now the question is, Why so? So this is because we have, the answer to this is, if we don't, then we fall into the dummy variable trap. Now what is this trap? Let me just illustrate. So in that two category example where we had education as, let's say, postgraduate and then less than postgraduate, okay, we used, so we had actually two categories. We used beta naught and then we used one dummy. Okay, now what did that dummy signify? So if this D was 1, it meant postgraduate. If it was 0, it means less than postgraduate. Now let me assume, for the sake of discussion, that what happens if I take two dummies. Okay, so then if Z1 is that one dummy, which is 1 if it is, if ith individual is postgraduate, and 0 if not, and Z2 is another dummy which is 1 if ith individual is less than a postgraduate, and 0 if it is if the ith individual is greater than a postgraduate. Okay, so then the model would be beta naught plus beta 1 Z1 plus beta 2 Z2. Okay, now if we have to write the model matrix, then what will it become? It will be 1 1 1 1 corresponding to the intercept term. Now let's say I have 5 individuals, okay, n equal to 5 individuals. So in that case I would have 5 1 2 3 4 5. Let's say individuals 2 and 3 are postgraduates. Okay, so then for beta 1, this column, only 2 and 3 will have 1s. Okay, and in beta 2, since 2 and 3 are postgraduate and Z2 is quantifying less than postgraduates as 1, then we will have 1 0 0 1 1. Okay, so this will be our model matrix. But now if you look carefully, you see that column 1 is actually equal to column 2 plus column 3. So this is a case of exact multicollinearity. Okay, where we have that the intercept term is exactly equal. What this implies is that the rank of this x is actually less than p, that is the number of parameters that we should to be estimated. Alright, so since rank x is less than p, then x prime x inverse, this will not be possible, and we will not get, we will not get unique solution, or we won't be able to invert x prime x. Okay, so that is the case why we should use one less dummy than the number of categories, because if we fail to do so, and if we take number of dummies equal to the number of categories, then we'll land up at exact multicollinearity, and that is not desirable. All right. Okay. So once we know that we should never use number of dummies equal to number of categories, then what is the go-to situation? So if I have m categories and if I am using an intercept model, then I should go for m-1 dummies. So in that postgraduate education level, in this example, here we'll use only one. So we'll have y equal to x beta plus epsilon. So it would be where the x matrix would be 1 1 1 1 corresponding to the beta naught intercept term, and 0 1 1 0 0 0 corresponding to beta 1 term. Okay, so then this z1 only would mean 1 if the category is, if that individual is more than a postgraduate, and it would be 0 if that individual is less than a postgraduate. Okay, so extending this example to the gender example that we had. So if we have male, female and other, so here we have 3 categories. So we'll go ahead to use 2 dummies. Okay, so that model will be beta naught plus beta 1 z1 plus beta 2 z2 plus epsilon. Okay, and then what will we have? So z1 z2 combination would then take care of everything. So if we had, let's say, 1 0, that means males. If we have z1 z2 as 0 1, then that would imply female. And if z1 z2 is actually 0 0, then this category stands for the other gender that we were talking about. Is it clear? Okay, fine. So this is the way to choose the number of dummy variables. Now, once we have chosen the number of dummy variables, next we have to see what is the sort of research question that we are trying to address. All right, so let's say we have the question in mind is that does educational level, or rather let me consider this simplest case where gender is actually male or female. So if I ask this question, that does gender affect initial salary or something like this. Okay, so what we mean to say is that if this is my graph, okay, and this besides, let's say, experience, so I'm going to plot income versus experience for males and for females. Okay, so now if let's say I have this thing, this is the line for males, and let's say this is, sorry, let's say this is the line for females. Okay, let's say this is for females, and this is the line for males, let's say. So if this is the scenario, then we can see that even with let's say some experience, 0 years, 1 year, 2 year, 3 year, 4 year, here we see that this difference we see some sort of difference in males and females in the intercept term. Okay, the slope remains same, but intercept changes. Okay, so if this is how the experience versus income looks like for males and females, then we can, from this sort of a setup, we will be able to conclude that yes, gender is affecting initial, I mean it actually plays a role besides experience. Okay, because initially we see a difference in intercept just because one person is belonging to one particular gender or not. Okay, so we could also have situations where we have a graph like this, where this is the graph for males, let's say, and this one, let's say, is the graph for females. Okay, so from these two, what do we see? We see that the intercept is the same, but the slopes differ. We are plotting experience versus income. Okay, so this could be another situation where the intercepts remain same, that is the initial salary on joining remains the same, but the slope differs as as experience increases. Females, for this particular example, females experience a steeper, the change in their salary or increment in their salary is more compared to males. Okay, there could be situations where both are changing. Okay, so that is this case. We are plotting experience versus salary, and if this is the line for males, let's say this is the line for females. So in such cases, we see that both slopes and intercepts differ. And the ideal situation that would have happened is that this this is the female's graph and this is the male graph, so both are same. So in this case, this is the ideal situation where both slope and intercept remains the same. Okay, so these four cases that actually arise, if we have to model these four cases, we have to use something like this. We have to use interaction with dummy variables. Okay, so how do we do that? How can we model interactions with dummy variables? So if we have something like this, let's say our model is y equal to alpha naught plus alpha 1 z1 plus beta naught plus beta 1 z1 into x. Okay, where z1 is 1 if male, 0 if female. X is actually years of experience. All right, so now if this is our model, here are the interaction terms. Okay, alpha 1 z1 this one and this one. So now if I put in values of 1 and 0 over here, then testing different hypotheses would lead to these different graphs. Okay, so if, let's say, if we go from here, from if we try to expand it, so what did we have? We had y equal to alpha naught plus alpha 1 z1 plus beta naught plus beta 1 z1 into x. All right, so let's say for males, what do we have? The equation becomes alpha naught plus alpha 1 plus beta naught plus beta 1 x. Okay, and for females it becomes alpha naught plus beta naught x. Okay, so if we have to model this case, that both are parallel. Okay, this is for males, this is for females. Then what do we have to test? We have to test that the slopes remain same. So we have to test beta 1 equal to 0. So if this term is set to 0, then the slope becomes beta naught x, and this is some alpha star, this is alpha naught, and they differ. All right. Second case, if we want to test for case 2, that um, this one, intercept remains same but slope increases. So in that case, we have to test for alpha 1 equal to 0. Okay, so if alpha 1 is 0, then intercept remains the same and we will have different slopes. Okay, and to test if both differ or not, we have to test for case 3, where we have something like this. Then the H naught is alpha 1 equal to beta 1 equal to 0. So if alpha 1 and beta 1 both are 0, then the lines are identical. Okay, but if one of them or both of them are non-zero, then we have this case. Alright, so these are the different ways how we can model interactions to get these kind of plots. So this is actually how we can use dummy variables to incorporate interaction with another x variable which could be continuous in nature. So here what are we doing? We are using this interaction term with this with the intercept coefficient or with the x coefficient. Okay, so in case we have this, okay, in case we have this situation and the final model is something like this, that alpha naught plus alpha 1 z1 plus beta naught plus beta 1 z1 into x. So if we have to solve this, we just need to get the appropriate model matrix, that is the capital X matrix, and it could have, let's say, 4 columns: alpha naught, alpha 1, beta naught and beta 1. So in alpha naught everything would be 1. Alpha 1 will be 1 for only those places where z1 equal to 1. So for the gender example, here and here, let's say the second and third gender is only this. And beta naught will have the x values x11, x12 to x1n, and beta naught 1 will feature those points where this z1 is actually 1. Okay, so this may be x12 over here, and here it could be x13, and then again 0. Okay, so this, if once we have a matrix like this, and also we should be very careful that we are not falling into the dummy variable trap. Okay, none of the columns add up to one another or something like that. So there should be no linear dependency between the columns. Once we are there, then we can just go ahead to use this model matrix and get our estimates. Alright, so is there any question from this week? Okay, so if we are good with this, then we can go ahead and solve a few problems. Alright, then let's just move on to solve a few problems. Okay, so here what they have said, we have two blocks of data. Let's say one is coming from set A and one comes from set B. Okay, so we have this thing, we can fit the model this, the LSE of beta 1 is approximately equal to how much? Okay, so then what should we do? This is our model. So the first step in solving or getting just give me a minute. So first thing is we'll just write down the model matrix, or yes, we'll just write down the model matrix. So now beta naught is present everywhere. So how many observations do we have? From here we have 4 observations. From here we have another 4 observations. So what are we going to do? We are going to keep it we are going to keep it stratified, in the sense that first we'll fit set A and then we'll write down set B. One thing that we should be very particular and mindful about is that we should definitely remember the order and how we are putting the data. Okay, if we put it otherwise, then also it will work, but then we have to be careful to put appropriate dummy variable components in places where they belong. All right, so here we have 8 observations in total. So for beta naught we are going to have 8 ones, 1 2 3 4. Okay, and then this would be 5 6 7 8. Okay, beta 1 will have only x values. So here we have 8 0 12 2, and then for the next set we have 9 7 8 and 6. Okay, so beta 1 and beta 2 is fixed. Now we'll jump to alpha naught. So alpha naught into z, so this will have values 1 only where z equal to 1. So z equal to 1 for set B. So we are going to have this as 0, 0, 0, 0 and 1, 1, 1, 1. So once we have this, next we have alpha 1. So for alpha 1, we are going to put x wherever z equal to 1. So alpha 1 would be 9786, again 0, 0, 0, 0. Okay, so if we have this thing, then beta hat OLS is actually x prime x inverse x prime y. So we'll see how to do this. So to do that, I'm going to take help of a software. I'm going to take help of R for the time being. So let me see. Let me just enter this into the model. Let me just make this entry into R as a matrix. So I'm going to stop presenting and then okay. Oh, so this one and this one. So once we have this, if I find out x equal to matrix I'm going to give the input as in the form of a vector. So I'm going to give 1, 1, 1, 1, 1, 1, 1, 1. I am filling column wise. Okay, then I have 8, 0, 12, 2. Again 9, 7, 8, 6. 9, 7, 8, 6. Okay, so this is column 2. Now column 3 will be 0, 0, 0, 0, 1, 1, 1, 1. So 0, 0, 0, 0, 1, 1, 1, 1. And the fourth one is again 4 zeros in front. 0, 0, sorry, 0, 0, 0, 0, and then we have 9, 7, 8, 6. Again 9, 7, 8, 6. Okay, so now I'm going to write by call equal to true, in row equal to 8 and in call equal to 4. Alright, so let me just run this. By default, actually this is actually this entry happens by columns, so I did not put it, but still. And since this was not working, I'll just see if by row equal to false. That is how I should, if I need to mention explicitly, I should write by row equal to false. Okay, so even then this X matrix will give me this form. Alright, so now that I have my X matrix, all I need to do is get alpha naught. So this is beta naught, beta 1, alpha naught and alpha 1. So now I am going to use x prime x inverse x prime y. So that would be x prime is transpose of x tx. Matrix multiplication will be percentage star percentage into x. Okay, so this part is actually x prime x. Now I want an inverse. In order to do an inverse, I should write solve of this thing. So this is doing x transpose x inverse, and then into again percentage star percentage x prime, that is transpose of x, again percentage into percentage y. Okay, and now what is y? Y is this vector. So I am going to input y, first set A and set B. So accordingly I have to put, that is 5.3, 0.9, 7.1, 2.4. Okay, and then again here 5.1, then 4.4, then 5.2, and then lastly 3.8. So this is, I have run, this is y, and now this thing is going to give me my beta. So you see, once I write this is actually my beta OLS. Alright, so this one is actually estimate. So estimates of beta 1 and estimates are as follows. These are the estimates of beta. Okay, so this is equal to beta hat. So the first one is the LSE of beta naught. This is beta naught hat. Second one is beta 1 hat. Third one is alpha naught hat, and the fourth one is alpha 1 hat. So from here beta 1 hat is actually option B, 0.506. Alright, so is there any doubt? Okay, fine. So let's move on to the next question then. The next question is the problem LSE of alpha 1 is how much? So alpha 1 is minus 0.036, the last one. Okay, so I think it'll have a minus sign over here. So this is alpha 1 minus 0.036. Okay, because that is what alpha 1 has come out. Alright, now let's move on to the next question. The question is, we consider the data in problem 1. So to see whether a single straight line model fit all data, we test alpha 1 equal to alpha naught equal to 0 against h1, h0 is not true. And what is the decision? So the model that we are trying to test is at h0 alpha 1 equal to alpha naught equal to 0 implies alpha 1 and alpha naught, if they are 0, then we have to use our restricted versus unrestricted sum of squares techniques. Alright, so the full model is how much? Full model is this thing. Okay, so full model, we have our beta estimates as this. Full model is, I'll write it down once again. Full model is y equal to beta naught plus beta 1 x plus alpha naught z plus this is alpha 1 xz plus epsilon. This is the full model. Okay, so beta is actually here beta naught, beta 1, alpha naught and alpha 1, and we have obtained beta hat. Okay, now under H naught we have the restricted model. We have the restricted model. Now what is that? If we set alpha 1 and alpha naught to 0, then we have y equal to beta naught plus beta 1 x. Okay, so then beta star is actually beta naught and beta 1. So let us just obtain beta star estimates. So in that case, what will we have? We'll have x star equal to x, but only we'll have a subset, it would be 8, no, not 8, it will be x 1 and 2. Okay, so this would be x prime one second, I should select all rows and the first two columns. Alright, so if I write this thing again, but remove the z terms. I could also subset it, but let's try this. So this thing is my x prime. Okay, so now if x prime is this, then beta star OLS is actually same thing, but instead of x we'll have x prime. Okay, so now this is my beta star. Okay, so this is beta, this is beta full, let's say, and this is beta restricted. Okay, so beta restricted is this much, 1.017 and 0.492. So here we have this thing, beta star sorry, we'll have here beta star hat as how much, 1.075, and here 0.492 3077 something. Okay. So this is beta star. Now in order to test this composite hypothesis, what have we learned? What is the usual method? The method is to calculate sum of squares due to residuals from the restricted minus sum of squares due to residuals from the unrestricted model or full model, sorry, sum of squares residuals from the full model, okay, divided by r, that is the number of parameters we are setting to 0, by ms residual of the full model. Okay, now ss residual is how much? We checked y prime y minus beta hat x prime y. Okay, this is what we have learned, x prime y. So this one becomes y prime y is how much? Y prime y, y prime y is 171.92, and minus beta 1 transpose x prime y. So that would be beta full transpose into x transpose into y. So that is 171.5928. 171.5928. Okay. This is for full. And then SS residual for restricted is y prime y minus beta star prime x star prime y. So this will be 171.92 minus this thing we are going to write. So instead of beta full and x, we will have beta r, that is restricted, into x prime into y. So that would be 171.4112. So this is 171.4112. Therefore, the test statistic is f restricted minus full. So this would be 171.92 minus 171.4112 minus 171.92 plus 171.5928 divided by number of parameters we are setting to 0 is 2, and by ms residual. Ms residual is how much? SS residual, that is 171.92 minus 171.4, sorry, 0.5928 ms residual divided by number of parameters we have estimated in the full model. So number of parameters we have estimated is actually 4, so it would be n minus 4. Okay, so now this is 171.5928 minus 171.4112 divided by 2 by 171.92 minus 171.5928 divided by 4. So let us just find out how much this is. So this is 171.5928 minus this divided by 2 into 4 divided by 2 into again this thing 171.92 minus full model, that is this thing. So how much does it amount to? Oh, sorry, this would be minus 411. So it is 1.11. So if statistic is 1.11. Alright, and the cutoff is f2, 4. Alright, so what should we do? Let's get the F table, or we don't need the F table for that matter, but still, if this is for alpha 0.05, F df 2 4 is actually 6.944. So this should be 6.944. If we want to get this from R, how will we get it? We'll have to write QF, okay, and then 0.05 lower dot tail equal to false, and df1 is equal to 2, df2 equal to 4. Okay, f in small. So that is also 6.944 as we saw. Now here, what was our rejection rule for these extra sum of squares? So extra sum of squares rejection rule was that we reject H naught if and only if F observed is greater than F cutoff. So here F observed is 1.11 and F cutoff is 6.944, okay, which is way greater than F observed. Therefore, we do not reject H naught, and that is our answer. Okay, so H naught is accepted. What does that mean? That H naught is accepted? It means that a single straight line model can fit all the data. So H naught being accepted interpretation is that a single straight line can fit all the data. So see, this is very similar to testing for this case. So we first assume that this is the scenario, and then we test these two things to show that okay, this is actually we can't accept this situation, but we are going to accept the ideal situation. Okay, so moving on. So here the question is, you have two sets of data involving values of x and y, but you are unsure whether to fit the data separately or together. Okay, so you consider and fit the 8 parameter model. So here how many parameters do we have? Alpha naught, alpha 1, alpha 2, alpha 3, again beta naught, beta 1, beta 2, beta 3, where z is a dummy variable, which is 0 for set A and 1 for set B. So what hypothesis would you test to answer this question? Will a single straight line model fit all the data? Okay, so let us just write down, break it down into simpler things, even though it is understandable, but still. So if it is from set A means z values are 0, then y becomes alpha naught plus alpha 1 x plus alpha 2 x1, alpha 2 x2 plus alpha 3 x3, and z into entire thing is 0 plus epsilon. Okay, and if it comes from set B, then the model becomes y equal to alpha naught plus beta naught plus alpha 1 plus beta 1 into x1 plus alpha 2 plus beta 2 into x2 plus alpha 3 plus beta 3 x3 plus epsilon. So to test whether a single straight line is going to model all data or not, we have to test beta naught equal to beta 1 plus, sorry, beta 1 equal to beta 2 equal to beta 3, and here we have to focus on this thing, that a straight line. Okay, so here we have three predictors. Okay, so if we have three predictors, then we are talking about a 3D prediction, predictor space. So we have to, so this multiple linear regression is sort of fitting a plane, a 3D plane, but we want a single line. Okay, so, oh sorry, this is actually, sorry, this actually should be square. Yes. So now just forget about this prediction space. So this is not something we would want to go into. So I'll just remove this. Yes. Now here we have x, and this would be x into x square, x is cube. So this one we have x into x square and then here we have x cube. Okay, so here they are asking, will a straight line model fit our data? So straight line means that x square and x cube terms should also not be there. So then that becomes equal to alpha 2 equal to alpha 3 equal to 0, and C is my correct answer. Is this okay? If so, then we'll move on to the next one. So now the distribution of test statistic to test the hypothesis in problem 4. So this one was problem 4. So the distribution of test statistic to test the hypothesis would be how much? Okay, so then what do we have? Full model is actually 8 parameters. Okay, and restricted model is how much? That is, we are setting 1 2 3 4 5 6 to 0. So we are left with two parameters. Okay, no, so restricted model, we are left with 2 parameters, and we are setting R. What is that? R is the number of parameters set to 0. So in this case, R it. So in this case, R, that is R, that is number of parameters we are setting to 0, that was how much? That is actually 8 minus 2, that is 6. Therefore, F statistic will have R into n minus number of parameters estimated in, so n minus p full. So that would be F 6 n minus 8, and that's option C. Okay, so full model, number of parameters estimated. Restricted model, number of parameters estimated. R would be the difference of 2, which means the number of parameters set to 0, and then degrees of freedom of F statistic would be R and n minus full, number of parameters estimated from the full model. Alright, so let's move on to the next one. Now, what hypothesis would you test to verify whether the models have same slope? So, if I am fitting a single straight line to fit all the data, then so given that a single straight line is fitting all the data, then to test whether we have same slope or not, all we need to test is beta 1 equal to 0. Okay, because see here, this is my y equal to mx and we are considering a straight line fit. So between the two models for set A and set B, if beta 1 is set to 0, then we'll have alpha 1x here, alpha 1x here. Alright, so the answer here is beta 1 is equal to 0. Okay. Just a second. Alright. So given that so now that we know this, let's move on to the next question. So now the distribution of the test statistic to test the hypothesis in problem 6 is so here we see that okay in the previous one, same slope one second. So slope coefficient is actually this one. Coefficient slope means coefficient of x. Alright, now coming back to this here. So the distribution of test statistic to test the problem in problem 6 is how much? Now if we are using h naught, beta, sorry, here for this one we are so for the last one we are considering a single line with same slope. So that means beta naught equal to beta 1 equal to so the thing is we are actually fitting a single line, and single line implies, or rather a line fit so if the question says that would you test to verify the models have the same slope, means that x cube x square terms are set to already 0. So then what do we have over here? We have a y equal to alpha naught plus alpha 1x, no, so here we have y equal to alpha 1 alpha naught plus alpha 1x plus, here we have z into beta naught plus z into beta 1x. Okay, and sorry, here alpha naught plus alpha 1x plus z into beta naught plus z into beta 1x. Now if we are following, if we are having the same slope, then we have to test that beta 1 equal to 0 on top of these things, that on top of testing, so single line straight line we were considering, so on top of that beta naught equal to beta 2 equal to beta 3 equal to beta naught, beta 1, beta 2, beta 3, 4. So here we have set A as alpha naught plus alpha 1 plus x plus alpha 2 x square plus alpha 3 x cube plus epsilon. Okay, and set B is actually alpha naught plus beta naught plus alpha 1 plus beta 1 x plus alpha 2 plus beta 2 x square plus alpha 3 plus beta 3 x cube plus epsilon. Okay, now slope means coefficient of x. So in this case, to test whether the slopes are same or not, we have to test for h naught beta 1 equal to 0. That is option B. Okay, and coming here, the distribution of the test statistic to test the hypothesis is this thing. So F will be, so F statistic will be R n minus P full. Okay, so P full is actually 8. Okay, and P restricted is how much? Is actually 7, because only beta 1 is set to 0. So therefore R will be 1. So the answer is that F will have 1 n minus 8 df. Okay, now let's move on to the next one. So here they are saying that data on a response y and k predictor variables x1 to xk arise from two factories A and B. It is desirable to fit a model of the form this. Okay, where Q denotes the factory in which the prediction will be made. In other words, the effects of x2 to xk are same in both factories, but intercept and slope with respect to x1 are different for each factory. The problem can be handled by using one dummy variable which takes the value 1 for A, 0 for B, and then fit the model which one. Okay, so here they are saying intercept and slope with respect to x1 are different. So if y is beta naught plus alpha naught z plus alpha 1 x1 z plus beta 1 x1 beta 1 q x1 plus beta 2 x2 plus beta k xk plus epsilon. So if I write the model as this, y equal to beta naught plus alpha naught z plus alpha 1 z plus beta 1 q x1 or rather I should write alpha so beta naught q. So for intercept this part is clear, because if we have z equal to 1, beta naught it will be beta naught plus alpha naught, and if we have z equal to 0, we'll have beta naught. Okay, so this is q dependent, so this part has been taken care of. Now x1, so if x1, let's say I'll write it in this alpha 1 z plus beta 1 into x1. So now if x if z is 0, then we have beta 1 x1, and if z is 1, we have some beta 1 star, which is equal to beta 1 q x1. Okay, so here again we see that this model actually corresponds to this one, option B, because whichever differs, intercept is differing, add one interaction term with intercept. Okay, one dummy with a constant term, interaction of a dummy and a constant term, then the intercept will vary, and slope with respect to x1 is varying, so we are going to add, apart from beta 1 x1, another alpha 1 x1 z. Okay, so this introduction of this interaction term and this interaction term actually takes care of my interactions. Similarly, if they would have said that it also varies with respect to x3, then we would have added something alpha 3z plus beta 3 into x3. Okay, so wherever it is varying, we are going to add that term, and then we are going to see, we are going to add an interaction term with a dummy variable at that position, and then go ahead for testing. All right, just stop. Okay, so this was all about dummy variables. We learned how to use dummy variables as an interaction term, how to model different scenarios where the response might depend on the dummy variable of interest, how to use how dummy variables can be used in the form, how we should incorporate dummy variables in our model matrix, so that when fitting categorical variables into our model, we need not bother much. Instead of x's being continuous, some of the x's will be categorical, it would be 0 1, and if we have interaction terms on top of that, then it'll be some places will be 0 and some places will be 1 into some, will have some sort of values. So, and then once we have our model matrix, getting the estimates and testing hypothesis is just similar to how we would have done a OLS regression. Okay, and then again, if after fitting, so the chronology is, if after fitting a dummy variable, so we know that there are predictors which are categorical, so then we go and find out how to model them. Okay, first thing is, how many categories do they have? The number of categories, if we are including an intercept term, then the number of categories minus 1 should be the number of dummy variables that we are including in the model. Now once we've decided on the number of dummy variables, we'll again cross check so that dummy variable we don't fall into dummy variable trap, that is, there is no multicollinearity in that X matrix. Once that is ensured, then we go ahead and fit an OLS regression, and then proceed similarly. If we have hypothesis to test, we do that. If we want confidence intervals, then we can do that, because these are all, so for single variable testings it would be t-test. To test a composite hypothesis like this, that this is 0, this is 0, this is 0, that would also imply the use of the extra sum of squares techniques. And then we fit a linear regression, we test for significance of the entire model or some coefficients. If we want, we get confidence intervals, and then finally we plot the residual plot. And then again, if we see that there is some problem in the residuals, then in the sense that it is not conforming to the OLS assumptions, then we can go ahead and we can transform the y variable, we can transform uh, we can make some other sorts of transformation, or we can just go ahead get an estimate of the variance covariance matrix like we had seen in the previous classes, and instead of OLS use a GLS fit, and then again proceed to testing. Okay, so this is how uh, standard regression modeling would happen. All right, so with that I'm going to end today's session. Thank you so much for listening and joining. I'll see you in the next class. Bye bye.